So, welcome to another episode from Spiral Physics Education. A little bit different this time. It's a grade booster episode. So, what we're going to be doing this time is looking at questions up to grade 6 sort of level, so they're relatively easy. We're going to be looking at questions a little bit harder than that, so aiming for grade 6 or 7, and also looking at the harder ones, so top end grade 7 to 9. All looking at stores and transfers. So to get the most out of this lesson, you're going to need to know what stores and transfers are and examples of those. You need to know the equation for calculating gravitational potential energy store and also for calculating kinetic energy store. And if you're not sure how to do any of those, do check out other videos on the channel. I'll help you do that. So let's start looking at up to a grade 6 base question. So this is going to be relatively straightforward. So we've got a 0.2 kilogram toy, and it's a spring-based toy, and when it's released, it reaches a height of 0.85 meters above the ground. So all the information is in that in that section there. And if we look at the units are correct. So we've got 0.2 kilograms, we've got 0.85 meters. We don't need to do anything else with the data there. And so it's a relatively easy introduction to this question. And when we look at the actual question, in the actual question itself, we are actually given the equation down at the bottom. So that makes it even easier. So for that reason, it's only worth 2 marks. And clearly all we need to do is use the equation and substitute in the values for mass, gravity, and height. So let's see how we can do that. So always, the first thing we always do is write the equation down anyway. So we're looking at gravitational potential energy. So just write that down, mgh, so we know what we're using. And then we can look for the mass, which is 0.2, g is 10, and the height difference is 0.85. Chuck that into the calculator, and we get 1.7, but don't forget the units, which can be joules, or capital J will do. So let's have a look at a question that's a little bit harder. So on the surface, it doesn't look like it's that much harder. So we've still got mass and we've got heights. The mass is in kilograms, the height's in meters. So we don't need to really worry about changing the units there. However, what we do have is a question that asks us to state the equation. So straight away, it's harder because you're being asked to write an equation down. And the second bit, we need to calculate the speed. Now, straight away, if it's worth 5 marks, there's a great deal to do there. So that's going to be quite demanding on students to get 5 marks there. We clearly have to do 5 things. And then finally, we're going to state any assumptions that we've made. And so let's go on with writing the equation now for the kinetic energy store. So we've got kinetic energy is a half mv squared, and it shouldn't be any surprise to you that that's straight away worth 1 mark. And now we're going to calculate the speed of the rock when it hits the beach. So it's a little bit more complicated. So we're going to have to write down or realise that gravitational potential energy is going to equal kinetic energy. So that's mgh is going to equal half mv squared. So we're going to have to do some rearranging here. So the first thing that we can do is notice that the masses cancel. That leaves us with gh equals half v squared. Let's multiply both sides by 2, so we can cancel out the half and the 2 on the right hand side. That leaves us with 2gh equals v squared. And now if we square root both sides, we get root 2gh is equal to the velocity. And now we can just straightforward substitute in our numbers. So we've got v equals the square root of 2 times g, which is 10, times the height, which is 55. So all of that is square rooted. And that is the square root of 1,100. And chucking that into a calculator, it's 33.162,479. Way too much on my calculator, but if I look, everything on there is given to two significant figures. So I'm just going to tidy that up to two significant figures. So 33 meters per second. Make sure we write the units down as well, because that could be worth a mark. Okay, so let's look at the hardest question in this sequence. So a question that's really based on students that are looking for above grade 7, mostly grade 9 on this. So we have a 20-gram stone thrown into a 100-gram box that hangs from the ceiling, and the stone is caught in the box and it swings upwards as shown below. Okay, so we've got a stone coming in from the left, lands in the box, and the box swings up and goes up in the air. And if we look at the question, after the stone lands in the box, it reaches a maximum height of 30 centimeters above its original position. So before we even look at what the question is going to be, this is giving you all the information that's going to lead up to the question. But straight away it's harder because the units are all wrong. We've got grams, which should be kilograms, and centimeters, and they should be meters. So one thing that you could do is just put a line through all of those and convert them straight away if you're one of those students that forgets to convert grams into kilograms and centimeters into meters during the calculations. So let's have a look at what the question is going to be. Okay, so we're going to need to calculate the speed of the stone just before it enters the box, and we're going to give the answer to two significant figures. So that's worth 6 marks. So we've got a great deal to do here. And the only bit of information or extra information we're given is that G is 10 newtons per kilogram. So not much help. So what we need to realise first, well, first thing that we need to realise is that the kinetic energy, or the original kinetic energy of the stone, is going to equal the increase in gravitational potential energy of the stone and the box. And that is just the conservation of energy. So we can work out the gravitational potential energy of the stone and the box using mgh. So it's going to be the mass of the box plus the mass of the stone times g times h. So the mass of the box and the stone together is 120, but we need to convert that into kilograms. So we need to divide that by 1,000. That's in kilograms now. Multiplied by 10 for g, and 30 centimeters, but 0.3 because we have to convert it into meters. Chuck that into our calculator. Well, step by step, 0.12 times 10 times 0.3, and that's a nice straightforward equation now to calculate 0.36 joules as our gravitational potential energy of the box. So the next step, so that's going to be worth a few marks doing that. So the next step in this is realizing that the kinetic energy of the stone, originally before it goes into the box, is going to equal all of that gravitational potential energy, i.e. 0.36 joules. So we can say 0.36 is equal to a half times the mass of the stone times the velocity squared. So rearranging that to get V or V squared on its own. And then next step, square root 2 times 0.36 over the mass of the stone. And from that, we get square root of 36. I'll just show you a missing step there, which might make it clearer. So the mass of the stone is 20 grams, so we have to convert that into kilograms. So it's going to be 20 divided by 1,000, which turns it into kilograms. And that's how we get root 36. And root 36 is 6 meters per second. Oh, but it says two significant figures, so technically it should be 6.0 meters per second for significant figures. Okay, let's have a look at the next part of that. So here we're not quite done with the box. The box swings back and forth with the stone inside. Describe the shape of the graph. So this is a describe question. And it doesn't. We've got no values on there, so we're not explaining, we're describing. And whenever you get a describe question, especially about graphs, it's always best to start off with saying basic information. So we're going to try and come up with a basic statement, and then we're going to try and get more complex statements just to build up to try and get all of those 3 marks. So we could say something along the lines of, as time increases, gravitational potential energy fluctuates, or it changes, or it varies, or it isn't constant. That's a very, very basic description of what's happening there. And now we can try to come up with a statement that's a little bit more advanced than just it changes. So a more advanced statement, well, if we look at the peak or the maximum values of the gravitational potential energy, each time there's a swing, that maximum value gets smaller or decreases. So we could say that the peak GPE gets smaller with each swing. Let's try a little bit more advanced. Oh, hang on. Let's delete that if I can spell advanced. There we go. So even more advanced. So if we look at each of the GPE, maximum GPE values, the difference between the first 2 peaks is large, and each of those drops then get smaller and smaller and smaller. So what we could say is that the decrease in the peak values is smaller and smaller and smaller with each swing. So it's not a constant, it's not a straight line, it's more like a curve going along those peaks. So that's more advanced. And we could also say, if we look at how long it takes for a swing, each swing takes one of those large boxes. So that could tell us if you're confident with the word time period, that the time period is constant, or that the frequency of the swing is constant. So we've managed to say 4 things there for a question that would only give us 3 marks. So we've got a good chance of getting those 3 marks there. Okay, so in then this next question, we're looking at explaining the shape of the graph, which is very different from describing. So why is it that the peaks get smaller and smaller and smaller? Well, one of the first things to realise is that we're dealing with the GPE decreasing. And we've got to try and realise that energy, if GPE decreases, conservation of energy says that can't happen. If something's decreasing, then something else is going to get bigger and bigger and bigger. So air resistance is acting on the box. So making some sort of reference to air resistance is the start of this question, about answering this question anyway. And the thing about air resistance, it's a force and it will do work on the box as it swings. clearly need to write faster. And if you're thinking about marks, you could always put bullet points on, although they always say that if you're going to use bullet points, you've got to try and make each of the bullet points link into each other. I'll just explain that in a moment when I finish writing this sentence. So in the first bullet point, it doesn't really, it's probably written too much there, but we can say that there's air resistance acting on the box. Next bullet point, I start off by linking from what I said to the first bullet point, this air resistance does work on the box. So that's going to be a mechanical transfer to take place because it's a force. And if there's a mechanical transfer taking place, my next bullet point can say that energy is transferred, and it's going to be transferred away from the box, but we need to say in a certain form or store. So it's going to be transferred to the surroundings. It's got to go away from the box. And whenever you say energy is transferred to the surroundings, it's usually going to be in the form of thermal energy. But what we can also say, to be a bit fancy, is energy is dissipated. The examiners love that. Energy is dissipated to the surroundings in the form of thermal energy. It kind of sounds scientific. So just to make sure that you realise in that sentence what the key words are. So it's really important getting dissipated, and where it's dissipated to the surroundings, which means we can't get it back, and that it's in thermal energy. So I hope you have found that episode useful, and you feel that you can use that to either improve your understanding of physics or improve your grades for this. So do come back to the channel and have a look at other videos, and I'll see you next time on Spiral Physics Education.